And we are back with the second part of problems 19a. So let's continue on. This is not going to cooperate. There we go. The 12C and D. In what temperature? Let me see if I can set my watch. Sorry. There. Let me see, what temperature range is it non-spontaneous? Now this non-spontaneous means that you'd have to force it to happen to freeze. So how would you force one propanol to freeze? Well, you'd have to have a temperature higher than -127 for this to be a non-spontaneous process. Remember, we're talking about freezing. Okay, is there any temperature at which liquid and solid 1-propanol is in equilibrium? Okay, I'm not sure how to explain this any better to say that once this 1-propanol, the substance is at its melting point, that means that it exists. If you remember what the cooling curve looks like for water, it comes up and then there's a place where it levels off and then it continues up again. This place right here is the melting point, and for 1-propanol, that's at a -127. Yeah, I don't know what I'm doing there. -127 degrees Celsius, and from here to here, the solid and the liquid exist all together in an equilibrium. And if you keep it at 127, you can have both the solid and the liquid together. Almost like having a glass of water with ice in it, and you keep the temperature, you put it like, I don't know, in a freezer, you can kind of, if your temperature is at 0 degrees Celsius, you can keep both of them there. Like you can keep both of it together in an equilibrium where some of it is changing into a solid and some of the solid is changing into a liquid. That is true. So, number 22, the element cesium freezes at 28.4 degrees Celsius and its molar enthalpy of fusion, which I believe this should be a delta H, is 2.09 kilojoules per mole. When molten cesium solidifies at its normal melting point, its entropy position is positive or negative. Okay, when it's going from a liquid to a solid, that means it's getting less random, which means negative. Okay, let me say that one more time. If you increase randomness, then you increase delta S, which means that it's positive. But if you're going from a liquid to a solid, that is decreasing randomness. That's R-A-N-D period, which means that you are decreasing delta S, which means that it's negative. Okay? So this right here is the answer. It would be negative. Calculate the entropy when 15 grams of cesium solidifies at 28.4 degrees. Excellent. What is this, number 22? Okay. So, in this case here, of course I need to know moles. Let me give myself a little bit more room to do this problem. For all of these, every time you're given number of grams of something, you're going to find the number of moles. So the first thing we do is find the number of moles of 15 grams of cesium. Cesium is 130, what is my problem? 132.9 grams. Okay, that's going to give us our number of moles. In the problem above, it told us, let's just keep this going so we can do all of this. The grams and the grams cancel. I'm left with moles. I'm going to continue on. This said, I believe, there it is, 2.09 kilojoules per mole. Okay, so I'm going to go 2.09 kilojoules on top so that I have moles on the bottom. kilojoules per mole, which is what this is, so I can cancel mole and moles like this. That's going to give me, 15 divided by 132.9 times 2.09 is going to give me a value that looks similar to this. 2, 3, looks like I'm going to have to, there we go, round off, should round off 3 places like that. And that's going to be kilojoules. Good. Now, unfortunately, we're not finished. This right here is only the heat part, which means the energy part, which means that if you guys remember, delta S equals Q over the temperature, Q over T, so the temperature in Kelvin, which means well, I tell you what, almost always we're given Q, in this case is measured in joules, and that will be per Kelvin. Okay, so I'm going to change this right here to 1, 2, 3. So 236 joules right here. 236 joules divided by, now we need to change this, 273. You can do 0.15, although I probably wouldn't. Okay, my timer has gone off. As soon as I'm finished with this part, then I'm going to be done with this problem. I'll be done with this part then. So that will be, what is that? That'll be 301.55 Kelvin. And then when I do that, I get 0.782 joules per Kelvin. And that's how you find entropy. This is a good problem to know because you'll be asked problems like this for Chapter 19. Excellent. On to the next part of Chapter 19A.